All right, here we are. Here's this box that I had talked about before. And here's some little wiggly lines that represent electromagnetic waves. Now, it's important to note that some of these are have long wavelengths and some of them have medium wavelengths and some of them have short wavelengths. That's because at temperatures all kinds of radiation is transmitted, and then here's this little window where the measurements are made. And so the next step is to figure out what are those measurements and how are they done. Here's the light coming out of the oven. That light coming out of the oven shines on a what's called a diffraction grating. This is a piece of glass with cuts of, well, the little scratches in the glass that allow the light to diffract into different frequencies, as you can see by these different colors. So if we can look at the different uh, modes of frequencies with a detector, then we can try and figure out some of this information that we've just been talking about. Okay, in the last few things, we looked at a black box with some waves going on, and we looked at the diffraction grating, which could split those waves up into different colors so that we can plot, according to temperature, which frequencies are existing there. That's what the whole exercise is for, trying to figure out what the difference between or what the relationship between temperature and frequencies are. So in this one, I'm going to do a little scribbling, and let's see if I can figure out where my pen is now. Select a pen, and I guess my color is going to be blue. And let's talk about what's going on here. Okay, what I'm going to do is scribble a wave. Whoops, sorry about that. And we're going to talk about this, and I'm going to use a math function along with this, and hopefully this doesn't scare you to death. Okay, I'm going to put an A, and that A is going to represent the distance from the center line of this wave to the top of the wave. So that's going to be my A. That's going to be the amplitude of this wave. And then I've got to describe what's going on with this as a function of time. It's a function of time. Let's see, how are we going to do that? Well, what I'm going to do is we'll start out slowly here. I'm going to use this word, sine, and this represents a waveform that looks like this. And the angles of that would go from, this would be 0, and this would be, rather than 360 degrees, this would be 2 pi. 2 pi. So between 0 and this is 2 pi. Now, why do we do that? That's because this is called radian angles, and that's the way it works out. And then this would be 4 pi, 6 pi. It would just keep going on like that. So now, how do I put the angle in here? Well, here's the way I'm going to put the angle in here. And this is going to be sine of 2 pi frequency times time. 2 pi frequency times time. That means when I go one cycle in a second, I've gone 2 pi radians. So that's how that sine thing figures it out. So if I do 1 cycle per second, in 1 second time occurs, then that's what's going on. And what I'm going to do is use a little different symbology. I'm going to say that or a sine and then I'm going to use a Greek letter omega and then t. So there I've got my wave described. So any point in time, I can tell you where the sine is based on the frequency times 2 pi. So I'm all done, right? No, I'm not done yet. I'm not done yet because this doesn't describe how this wave is moving away from the black body. Let's make instead of let's see. I'll put a big square here. This is the box where this is going on, and the box I'm going to say has a length L on the side. So the total volume of this box or cube is going to be L cubed. Length times width times height, it's all the same. So the volume is L cubed. And then I have this one little spot in here. I'll call this the black body that's radiating. And the waves are moving away from this center point. Now, how do I describe things that are moving away from that center point? Because it's three-dimensional. It's three-dimensional. So what I'm going to do is put a vector here. Now, what in the heck is a vector? Well, a vector has length, so it tells me the length away from that spot, and then it has direction, and that direction can be in 3 dimensions. It can be up, down, or into the page, if you want to think of it that way, but can only show 2 dimensions here on this. And let's see what's going on. So the wave is moving in this direction, and I'm going to call this an R. There's the R vector, and I can put a little arrow over the top of that to show that it's a vector. All right. Now, let's see what we can do with that. So I can describe the wave according to how this R thing proceeds. As time goes on, or as I move away from the center, the wave I'm going to see different parts of this wave that's moving through space. Even though it's always changing, I have to involve this R thing that gets involved. So I'm going to modify this to include that. Put an arrow, say down here for this one, and hopefully I can still draw correctly with this thing. Here's sine. And in this case, I'm going to put something that relates to this vector so I can describe the wave as it moves away. Sometimes we just say, if I'm standing still and look at a wave, then I can look at it this way. If I'm standing still, this is what the wave looks like. If I move out from that, though, I still have to include the R vector. And what I'm going to do is something very strange. I'm going to put a 2 pi. There's that 2 pi thing again. And I'm going to divide by, and then I'm going to use a symbol for wavelength, which is the Greek letter lambda. So I'm going to put 2 pi over lambda, and that I'm going to multiply that times r. And this is my vector r. Then I'm going to say, and this looks a little strange here, but I'm going to say minus omega t. And if you look at this now, then it looks like this r is involved here. If time's not moving, if time isn't moving, then I can still look at that wave. Well, time's not moving, then we don't have any waves. It's a little hard to say time's not moving. But this takes into effect what's going on with this thing. Now I'm going to put another little symbol here and rewrite this or, put the or there, a sine, this is trig, sorry about that, but we got to use some trig here. And I'm going to put k and make this k a vector as well. Then I'm going to multiply the k times the r vector. Now, where did the k come from? The k came from this 2 pi over the wavelengths. Now, you can see that this factors in the fact that if I move one wavelength, I've moved 2 pi. One wavelength is going to equal the 2 pi. Oh, a wavelength? Here, let's do a wavelength. A wavelength would be between, let's say, the top of this and the top of this one. So that would be one wavelength, whereas this one was amplitude. Amplitude was over here. It's getting a little small there, but I think we can work that out. And then the final result that I'm going to get to on this one is, and this seems like we're getting nowhere, doesn't it? It seems like we're getting nowhere. But this is all going to come out in the wash, and we're going to be able to come up with this formula that we saw on the previous video. Uh, well, I think it was the second earliest previous video that the people that were doing this research were using as their equation to describe the reality. So let's stop on this one and we can proceed. But this next one, next step here, I'm going to start with this thing and hopefully we can understand this a little bit from what I just described.